So what we've been going through as we've been kind of going through this history of astronomy, how we've gotten to modern ideas, is essentially the scientific method. I'm going to guess that you've probably talked about the scientific method previously in some other course in junior high or high school, but just to make sure, we're going to go through it one more time, although not very quickly. So it all begins with some sort of observation. You see something about the universe that you don't understand and you want to understand it better, so you begin to ask questions and gather data about that thing. Once you have enough data, you can then form a hypothesis. One great working definition of hypothesis is an educated guess based off of all of the evidence you have. And that is a great definition. It's probably the definition that most of you have used for hypothesis. There's actually another definition that I prefer. You may be familiar with the kids show Dinosaur Train. For those of you who aren't, this is a PBS kids show teaching kids about paleontology, about dinosaurs and so on. So the premise is that we're following a family of dinosaurs that travel on a train which can go through time so that they can then go and visit other species of dinosaurs in different eras when dinosaurs existed. We've got dinosaurs, trains, and time travel. This could be the best kid show ever. Well, if you aren't familiar with it, I'm pretty sure it's still on Netflix. If not, you can go look it up on pbs.org. Anyway, in that show, it is trying to teach scientific principles. We will ignore the fact that the dinosaurs are speaking English and have trains and time travel, but those are just ways to help teach other scientific principles. Occasionally on the show, one of the dinosaurs will say, "I have a hypothesis," to which one of the other dinosaurs will respond, "You mean an idea you can test." That's the definition of hypothesis I prefer. It is true that a hypothesis is an educated guess based on your data, but it must be testable, meaning it needs to be able to make predictions. If it does not make predictions, then it's not a hypothesis. We need to be able to find out if our idea is correct. So we form a hypothesis. It then makes some kind of prediction. We can then formulate some sort of experiment or observation that will then test that prediction. If we go through and we find that our prediction is wrong, that means we now have more evidence. We have more data, so we can then revise our hypothesis. If we go through and we find out that our hypothesis is correct, our prediction matches matches the experiment, then we're good, and we then go and find other predictions made by our hypothesis. And so I hope that you've seen some of these things previously. Now, some things that I want to point out. It is often taught that the scientific method is exactly the way that you do science. That is not true. Science actually goes in very different ways. This is the idealization, meaning this is the way, the general flow of how science works. Some examples of how science does not progress through the scientific method is scientists. Scientists are people, and therefore they have all of the benefits and flaws that people do. Scientists' intuition can actually help play a large role in discovery. For example, I've seen several times where a scientist will be going in one direction and it just feels wrong to them, and then they'll rearrange, look at the data in a new way, and all of a sudden everything comes through. There's nothing about that in the scientific method. Another piece that can get in the way in this case is that all people are biased. A bias is a preferred worldview. And so, as you're doing experiments, all you do is collect data. Then you, as the scientist, need to look at the data and then interpret it, trying to come up with what does this data actually mean. As you're going through that process of interpreting data, it is very easy to make the data fit your preferred worldview. One of the hardest things that scientists have to do is to set aside their bias and to look for what the data is actually saying. And so, again, there's nothing about that in the scientific method. So it's just an idealization, although it does generally flow in this way. Now, some characteristics of science generally. Science tries to explain things through natural cause and effect. If you remember previously when we talked about the ancient Greeks, this is one of the things that we get from them. We try to explain things in natural ways, not invoking the supernatural. Science explains phenomena in the simplest way possible. Now, I know what you're thinking. You've heard some of these scientific theories, and they sound anything but simple. They actually sound very, very complicated. Now, in this case, what's going on is that a scientific model has to include all the available data. It'd be really easy to make very simple ideas if you ignore all of the inconvenient data. So, because we've got this other information that we must also include into our models and our theories, we have to manipulate and change, and things become more complex. Then the last characteristic is that a model must make testable predictions. If you can't test it to see if it's correct or not, then it is just philosophy. I shouldn't say just philosophy. The last thing is that a model must make testable predictions. If it's not testable, then it is philosophy. You can debate the merits of the idea, but if you want to see if it's the way that the world actually works, you have to be able to test if that's what's going on. Now, this idea that the simplest explanation is often the correct one is what is known as Occam's razor. It is named after Occam, and it is a razor in that it cuts away the more extravagant, the more complicated ideas. Okay, it's actually this idea that the simplest explanation is often correct is part of the reason why the Copernican model, the first heliocentric model, held on. Its predictions were bad, just as bad as the old Ptolemaic models, but it was simpler, and because it was simpler, people held on to it. Now, if we have a powerful yet simple model that can make many predictions that keeps standing up to multiple tests over a long period of time, then we refer to it as a theory. Okay, so you may have heard the phrase, "Oh, it's just a theory." Hey, that's often something we say to mean, "Oh, it's just an idea, I don't know if it's right or not." Hey, "Oh, it's just a theory." Well, in science, if something has progressed to the point that is a theory, this means that there's actually a lot of evidence in support, that it's actually making good and testable predictions. One example of this is the theory of general relativity. The theory of general relativity is our current understanding of how it is that gravity behaves and how it works. This was first introduced by Einstein in 1915, and since then it has been constantly challenged and tested. And even though it's constantly being tested, every single time that we test it, it has come out correct. So we refer to it as a theory because it's continuing to be tested, but now we pretty much assume that it's going to give us the correct answers, that it is good and solid. Alright, here is our 5th lecture quiz question. In science, a theory, A, is just an idea that is yet to be tested. B is an idea that has been tested and shown to work in most circumstances. C is an idea that has been tested so thoroughly as to no longer be questioned. Or D is an idea that has been shown to be completely true. Go ahead and think about it, and we'll discuss in just a bit. Alright, so in theory, it is not just a theory, it has been tested and keeps working. Although, theories are never proved. They're actually always we're always testing them to see if they're correct. So the answer is B. It's an idea that has been tested and shown to work in most circumstances, although we may still be trying to find those exceptions to where it works. Now, something that I want to point out is this idea of astrology. And, there was actually a poll done, now it's been probably over 10 years ago, but seeing the general public's opinion of varying sciences, how trustworthy they felt the sciences were. And things like physics and chemistry kept getting in the 80s and 90% of, we trust what they're teaching us. But astronomy kept getting somewhere in the 40s or 50s, and people kept wondering why this was. Astronomy is actually based a lot in physics, so why is astronomy viewed so poorly? And then somebody realized people are confusing astronomy and astrology. Astronomy is the science, astrology is the belief that you can predict the future or be able to understand a person and their personality based off of the motion of stars and where the motion of planets, not stars, the motion of planets and where the sun, moon, and planets were in the sky on the day that they were born. Okay, so make sure you do not confuse astronomy and astrology. Astrology is actually a pseudoscience. What that means is it has a lot of the characteristics or a lot of the things, the words that we often use in science, but it's ignoring some of those key aspects. For example, one of the big problems with astrology is they can actually make testable predictions, like science does. However, when we go through and we actually test their predictions, they are correct no more than random chance, which means that it's probably no better than just random chance at getting a correct answer. Okay, it's probably not actually working. But to an astrologer, they keep coming up with other ways of explaining away the data that they don't like. So it's similar to science, using a lot of the same words, but it's not actually keeping all of the aspects of science.